All right, it's 11:30. Let's begin. So, change in plan for the quiz. It's still going to be today. It's just the last 15 minutes of the class. So that way, if anybody uses extra time, it's not going to interfere with them learning the next piece of material. All right, so that's how we're going to do quizzes from now on. Now, help me. Just remind me when it gets like 5-2. All right, 5 minutes to the last 15 minutes of class. So that would be 12:25. All right. All good? All right. So next topic is piping. All right. Piping refers to any assembly of pipes, tubes, valves, fittings that form all or part of a system for the conveyance of fluids. All right. Pipe refers to the non-flexible fluid conductors designated by diameter and wall thickness, strength, or schedule. Most of the time you will hear it as schedule. All right. Tubing can be and usually is bent at installation. It's more flexible than pipe and is designated by nominal outside diameter and wall thickness. Fittings. Fittings are devices employed to join sections of pipe, tubes, or hoses in a piping system. All right. Now, nominal pipe size, or NPS, is an approximate inside diameter of a standard pipe. All right, so Schedule 40. So, example, we have a 3-inch standard pipe. All right, its outer diameter is 3.5 inches. All right, its inner diameter is 3 inches. Its wall thickness, all right here, 0.216. If we go up to Schedule 80, this is a Schedule 40. All right, the outer diameter is still 3.5 inches. Its inner diameter now is a 2.90. All right. And then we have a 3-inch Schedule 160. All right. Wall thickness of 0.483. Notice how the outside diameter has not changed. All right. Only the thickness of the wall has changed.
Professor,
What's up?
when you're talking about pipes in general, you use the inside diameter, correct? Like just a standard pipe and the thickness. But
It's so yes, it depends. A lot of the time, what you're going to be talking about is what you're talking about is schedule.
okay.
That's for the thickness. That's basically no one's going to be talking about a 0.216 thick wall. All right, everyone's going to bring up what schedule it is. When you get into the crazies, all right, which I'll bring up in a second, the crazy world of wall thickness, that's when people start talking about wall thickness. All right, and the outside diameter. All right, and why I bring that up is because I worked on a dredge ship. And on a dredge ship, we sandblast all of our equipment 24 hours a day, 7 days a week, 365 days a year, because that's our job. We move sand from one spot to another. All right. The entire ship is basically a giant sand vacuum cleaner. All right. We had about anywhere ranging from a 6-foot diameter pipe down to something that was 3 feet diameter. All right. We had 3-inch armor plated steel wall thickness. All right. That was done because we were sandblasting everything, always, continuously. All right. Within 6 months, we were down to 0.25 of an inch. We went
Holy
from three
shit.
inches down to 0.25 within 6 months on some of our steel. All right. So we had to do what was called a UT scan every 6 inches on our pipe. We had a lot of pipe. That was not a fun time. I did a lot of it. So you basically went around, you would grind off a little tiny section because you couldn't use paint. Paint would interfere with it. You would grind it off. You would take this little UT scanner. It was the size of, about that big. and you put on basically some jelly that would go onto it, and you would scan the wall thickness every 6 inches. All right.
Excuse me?
What's up?
Would you do this while the ship's underway or while it's not?
All the time.
Okay.
Wait, so how do you replace the pipe then if it's that, like if it's thicker, would you just like add like a layer to it or
Sometimes we
what
had
would you?
to. So if we were doing the job that it was able to, and that's why it was important to, here, I'll go to this page.
Like a sheath or something on it?
So that's why it was important that we did these UT scans, because sometimes we would develop a hole or a crack, or that was a hole on our pipe. All right. And this is our whole side of our pipe wall. All right. And what we would have to do is we would have to scan all around this pipe, this crack. All right. And in doing so, we had to find a spot where we can weld to. All right. So we would grind off this entire area of what we would find. We would need at least 1/4 of an inch to weld. All right. And we would find all that. Sometimes this crack would be here, but we would have to put on a 2-foot by 2-foot plate.
Oh, until you find like the actual like until it's thick enough, right? And then you can just
Until we can actually weld to it. Exactly. All right. And sometimes when we would grind off paint, guys, we would find little micro holes, little cracks, things like that would develop. It would really throw a wrench in your plan of where you thought you were going to be able to weld to this. All right. Most of the time, what would happen is if the crack was bad enough, which we've had some really bad cracks, it would shut down the job. And we would have to basically get our welder, which God knows it was always 2 o'clock in the morning when I had to go wake him up. It never happened during the day. And we would have to shut down the entire ship and weld until it was fixed. A lot of times we had to go in the shipyard.
Quick question.
Yep.
So like a Schedule 40 pipe would be a 3-inch diameter or a 3-inch thickness?
So it's not thickness. So Schedule 40 is all about the wall thickness. All right. The larger the number, the more the wall thickness increases. All right. So you can see a Schedule 160 has a 1/2 inch wall thickness. All right. Where Schedule 80 is only 0.3, but it's a ratio to what the actual pipe is.
Oh, it's not an actual number, it's just the ratio to the size of the pipe, right?
Pretty much.
Okay.
Gotcha.
All right. Because if you had like a 1/4 inch pipe, right, and it was Schedule 40, well, wall thickness of 0.25 is pretty close. So it's always going to be, it's a ratio off of what it is. All right. So Schedule 40 is always going to be the smallest, but it's standard. All right. And then you go up to higher and higher and higher. All right. For pipes with an outer diameter that is greater than 12 inches or equal to, it is done by the outside diameter. All right. So Schedule 30 of a 16-inch pipe, all right, the outer diameter is 16 inches where the inner diameter gets smaller. All right, and so on and so forth. So Schedule 40 basically has a full 1/2 inch thick wall. All right, and then Schedule 160 goes down to 1.5 inch thick wall. All right. Notice again, this has not changed. This outside diameter. All right. So outside diameter in 16ths or 16ths. Number 12 tube has an outside diameter of 3/4 of an inch. A number 16 has an outside diameter of 1 inch. Most of the time, people are just going to basically not go with, number 16 or number 12. It's going to be a lot of just basically its outside diameter, or also this wire gauge. Okay, they'll be talked about. All right, so the wall thickness is in a decimal or in the BWG wire gauge number. All right, so same thing. 18 as wire gauge. 18 is going to be a small wire. 18 is going to be a thin walled. Or if you have a 12 gauge, it's going to be a thicker wire. or it's going to be 12. It's going to be a thicker walled. All right. So the smaller the number on this wire gauge, the thicker the wall, and it's going to be the thicker the wire. All right. The higher the number, it's going to be a thinner wall, and it's going to be a smaller diameter wire. All right. So it operates in the same instance as that. Copper tubing kind of falls into its own category in itself. All right. So it's still considered tubing. It's not really pipe, but it also utilizes fittings, whereas tubes utilize bends in order to go like 90 degrees. Copper tubing can utilize either bending, or it also could use fittings. So it is in its own category of both. All right. It's designated by slightly different parameters as well. All right. So it utilizes the nominal outside diameter. All right. So a 1-inch copper tubing has an outer diameter of 1.125. All right. It's called a 1-inch pipe. Same with 3/4, 1/2 inch, all that kind of other fun stuff. Wall thickness is not designated by anything other than a letter. So K, L, or M, with K being the most robust. All right. So it has a thicker wall. The material that it's made out of can take a little bit more of a hit. The example I use is that I just had to replace a 1/2 inch copper line in my garage. It goes to a water spigot. And because it's exposed, one, I wanted a tougher type of copper, so I went with K because it's outside. All right, it's not fully outside, it's in the garage. It's an attached garage. But if we forget to turn the water off in the winter, it will have a lower chance of freezing and busting the pipe open because it's using a thicker wall, can take more forces. All right. The other thing is that it's exposed, so it can get damaged, and we don't want this thing to get all banged up. So when we hang things, enter the car in, stuff like that. So we went with a type K so it can take those damages. So things to think about. It's not just about wall thickness, but what it's going to stand up to. All right.
So, question: we use mostly the K.
Say again.
We use mostly the K, since it is it could be outside.
I'm sorry. Say again. You're breaking up as you're talking.
I'm saying, so we use mostly the type K.
So I would want more type K.
We use mostly the type K.
So yeah, I used all type K in it, in that piping. All right, it's the most robust of it. All right. So piping connections. All right, we can weld them. All right, this is called a butt weld. It utilizes a V groove. All right, it's grooved out at about a 45-degree angle. Most of the time when you buy a piece of pipe, both ends will be V grooved. All right, unless otherwise designated. All right, you would have to go buy something that's not V grooved. All right. If you cut a piece of pipe to length, you'll have to V groove it out yourself. There's no special tool. It's a grinder. All right. And this V groove is there for a specific reason. All right. It allows you to stick an actual welding stick into the area. All right. It gives you more surface area to get that weld on. If you were to just weld on two pieces of material flat up against each other, you would not have enough surface area and it wouldn't give a nice deep hold. Right? You wouldn't have enough penetration into both sides of the metal. All right.
Mr. Callahan,
What's happening?
would you say that V groove might make the weld a little bit weaker, considering it's not completely welded straight through?
What do you mean that it's not?
Yeah, because the way I'm looking at it is like that groove there.
Mm-hmm.
Being if it was like completely welded from one side to the other, I would think that groove being there might not make the weld as structurally
Strong?
yeah.
Okay. So when you weld, guys, who here is actually either taking the class in welding or had welding experience?
I have.
All right.
I have.
It's in your garage, or did you take a class?
Garage.
The Coast Guard yard.
Coast Guard yard?
Ooh.
All right. So no one here has actually physically taken a welding class.
I took
That's
it at
I
Pasco
did.
as well.
So Frank, and then there was someone else I heard.
Me.
Yeah, I took
Nicholas.
one.
Carry on.
And someone else.
Nick Smith.
Nick Smith, Harry. All right. So did you
I
guys?
did.
Okay. Yep. Now I see you now. Okay. So when you guys took your actual welding class, did you do any braking test?
Yeah.
All right. Where did
Yeah.
the weld break? Where did the actual, if you did a T weld, right? Like that, and you welded on both sides. When you did a braking test on this, where did it actually physically break?
Oh, it would break on like either one of the sides of the weld, so it wouldn't break down the middle. Like it would break. Like
So it would break over here, right?
yeah,
Yeah.
On
yeah.
the side.
So it would never break on the, when you did it and you got an actual completion, right? It would never break the weld. You would fail if you broke the weld, right?
Yeah.
All right. Why was that? Why was it a failure when you broke the weld and not when you were breaking any other the metal?
Because then your weld is faulty.
Yeah, it's like strength integrity. It's a little
That's the part of the testing.
As part of the testing, right? So when you're in the basic welding, the biggest thing that you learn from it is that your weld needs to be stronger than the actual material that it's going onto, right? That's why it always breaks, not at the weld. And if it's breaking at the weld, then you have a faulty weld, right? So that's the same thing that's being applied here, okay? So it will actually make it stronger with the weld here in this area. It gives you the surface area and also the penetration. You're trying to penetrate into the metal. Welding is not just based on the surface of that area. All right, the weld just doesn't insert into that area and don't exist only in that little tiny section. The weld itself penetrates into the metal. All right, and that's why everybody would have breakage on either side of it, not physically on the weld itself. All right, so that's why that V-groove is important. It gives that surface area, because if you just had two flat pieces of metal butted up against each other like that, you would only be able to get a weld in there and barely get anything in there. You would just have a surface weld. All right, but with the ability to V-groove it, you have all of that area now to get deep into it and weld that area up.
Okay.
All right. So that's what's happening.
So a wider area equals a stronger weld?
Not always. It's not like you're going to have like a 22-degree angle where you would have like this long bead like that. But there is a point of no return. So just given that surface area, you'll be better. And a lot of the times you can actually have spots where you would do a triple weld like that. Right, where you'd have a base bead and then you would put on two more beads to increase your surface area and spread it out.
Okay.
All right.
Got it. Thank you.
That was a good question. All right. There's something here called a backing ring. Excuse me, a backing ring. All right. Anybody who's taken the welding class, you can say different, but never in my life have I seen a welder or myself has used a backing ring. All right.
never.
So backing rings are basically there as to, from what I can tell in my own research, like I said, they just kind of keep the weld there. But in reality, they are consumable. You can't reuse them, all right? Because if you're welding a pipe together, are you going to be able to reach in there and grab that backing ring out?
No.
So
Nope.
it's pretty much worthless. I've never seen anybody use it, all right? So the weld itself is in there. It goes all the way around the pipe. It's in that V-groove, all right? Another way, which you tend to see a little bit more these days, Not so much of these V grooves. They still exist, but has some sort of a collar. All right, so you can see that there's no V groove. You can cut piping as easy. You don't have to worry about grinding anything away. It's just a straight cut and welded up. All right. Now you can see right here that there's a little space. There's a little air gap there. What is that for?
For a seal or a gasket, maybe?
Nope, it's not for a seal or gasket. You remember, this is the actual seal. There is no gasket. This is a welded seal.
Is that for the weld to seep in a little bit, like to get into the actual
Is it so it doesn't bind
pipe
there?
area?
Like replace it if you need to, I guess.
Not for replacement. It's not for the weld to seep in. So if the weld seeped in here, you could have a problem where you could have like a weld dripping in, right? So you would block your flow.
Does it have to do with expansion and contraction with temperature?
Exactly. Just that little bit of room for expansion. All right. If you're turning on, this is a boiler, all right, coming out of here. We have 600-pound steam coming out. All right. Turning on for the first time. That engine room could be anything. Let's say it's summertime. All right. More than likely, it's a cold ship. It's probably 70 degrees, this piping. It's cold. All right. To the touch, it feels cold. We have 600 degrees steam coming right through this. What's going to heat up first? The piping or the fitting?
Yeah, the piping.
The piping. And it'll be a gradual heating up, right? It's not going to all be instantaneous. All right. So it just gives that little bit of room for expansion. All right. Granted, these are still the same type of material. They'll expand at the same rate, but one's going to be hit with heat before the other. All right. And it's not much. It's like a 1/16 of an inch. All right. So going through with it, you can see the weld goes across the top right there. All right. And that's the name of it, a fillet weld right there. All right. A lot of the times you'll actually see you'll have an initial weld there. And like I said, you'll have a triple weld that will go on this type of fitting. All right. It makes it stronger. It usually seals up a lot better. It lasts a lot longer if you do that triple. All right. Now we have threaded. All right. So threaded is using the American National Taper Pipe Thread, or NPT. It is not the same as a machine thread for bolts, nuts, and all that kind of stuff. We notice we actually have a slight taper to our threads as well. All right. Now, for nuts, bolts, machine threads, all right, that's TPI for anybody who's curious. Threads per inch. All right. So external threads on here are cut with what's called a die, D-I-E. It utilizes internal threads to cut the external threads of a pipe. All right. So if you ever made your way into the machine shop on the ship or in the classroom on land, you'll see these hanging on the wall. That's basically where the die gets inserted. They are ratcheting, all right, so that way you don't have to swing these things around. They tend to be very big and large, all right, because cutting taps and cutting threads is not the easiest thing in the world, all right, so you'd need a lot of leverage, all right. And then you have what's called a tap, all right. Taps cut with an external thread to make internal threads, all right. And we can see right here in this space and in this space, we're missing threads. It's actually pulled back away. Why do we have that?
So the metal shavings can get stored in there while it's being tightened and loosened so that it doesn't affect the threads being cut.
Exactly. All right. So we're removing material. It just doesn't poof off and go to Netherland. All right. We are removing it. It needs to go somewhere. All right. That's our threaded. And now we have flanged. All right. Flange is usually what you'll see the most on high pressure and low pressure systems, especially if it was built by the shipyard. All right. They tend to be Welded is for fittings and stuff like that, but for like straight pipe, you usually tend to use flange. All right. So flanges are great, but they are kind of in their own little specialty. All right. So they can be threaded on, they can be welded on, they can be welded with a neck to it. You can see that this is our actual flange and this is our piping over here with the weld over here. Whereas on this one, the flange collar goes over the pipe and it's welded on both sides. All right, and then over here, you can see that the flange goes all the way down to the pipe and it has a stopper on the end of the pipe. All right. Now, with flange comes gaskets. All right, this is the spot where we see our first gaskets. All right, so for LP, low pressure, all right, you can use rubber, paper, flexible graphite, synthetics, things like that. All right. For paper, world's best gasket material for paper is charts, old charts. So if there's any mates in training here, all right, and someone comes asking you for chart paper that's an engineer, don't be alarmed. This is what they want to use it for. It makes fantastic gasket materials. All right. And if you need a wrapping paper, it does really well for wrapping paper too. So they are done with bolts and nuts. All right. Now you can see the animation there. Watch the animation on this side. You see how those are turning gray? And they're going in what's called a star pattern. Why are we not just going in a clockwise pattern? Why would we go in the opposites?
It needs to seat properly.
Exactly.
Even.
And so it's even.
Yeah, even tension, like on a wheel on a car.
Exactly. If we didn't do that and we had two flanges like this, all right, we did all the bottom ones first, we would end up splitting it and making it a V, and now all the fluid is just going to come out of the top, all right, or the bottom, whatever side you decide to start on. All right, so it has a bolting pattern, not only for insertion, but also when you are actually tightening it down or torquing it down. All right. Low pressure sides can use a bolt and nut. You can also use a stud with two nuts on either side. But with high pressure, you have to use studs. All right. Again, here's your bolting pattern. The 1, 2, 3, 4, 5, 6, 7, 8 right there. All right. Pretty much a star pattern. All right. Always just do your opposites. All right. Now, here's the big difference between the two. We have a high pressure and we have a low pressure. High pressure uses a different type of material, metallic or flexitalic. Flexitalic is a branded one. All right, but here's the other big difference we can see. The gasket material for a low pressure on the flange takes up the entirety of the flange. Whereas with the high pressure side, all right, we can see we have a little bit of a raised piece of metal on both sides where the gasket material is actually making contact. All right, that's where the seal is happening, not anywhere near any of the bolting areas. Whereas with the low pressure, the seal is happening in the entirety of that gasket. All right. Stop it. There we go. So just be aware with that. All right. And again, this is utilizing studs. All right. And should use the same torquing or tightening sequence. Any questions on flanges?
What do you mean by studs? Like studs on like a car on a wheel bearing, like lug nut studs or whatever, where they press in, or?
So studs utilize, it's basically a threaded piece of rod, all right, that utilizes nuts on both sides.
And why do they do this? Just do they like so they don't back off, or?
Basically, it's not that it's going to back off. You would have to double nut it for it to stop it from backing off. All right. But basically, it comes down to the fact that the bolt head is going to be its machine part of it. All right. Usually, the studs can handle a stronger pressure. All right, because it's going to be trying to push out on both sides. So this one's going to be utilizing the actual threads to keep its strength. Right?
Oh, equal pressure on both sides, right? With the stud, so it evens. I guess it makes yeah, I can see how. And
then the other thing on the bolt is you can't tighten down on the bolt side. All right, you only can put a wrench on it while you tighten down on the nut. All right, to hold it. Yes, it's equal pressure, but also at the same time, you can tighten down both sides of this stud with that threaded rod, and it will tighten it even more. It can handle the higher pressures. All right. All right, guys, if you have any questions, feel free to stop me. All right. And ask it. Don't wait for me to ask if there's any questions. Sometimes I just don't. Tube installations are never straight runs. Deliberate bends allow for a reduction in length, which can occur as the tube is pressurized. All right, think about it. We are training to be engineers on a ship, not on land, right? So what happens when you're on a ship and that ship hits a wave and all the way in the bow and the engine room's way back here in the engine room? What happens to the ship? Is it all going to move at the exact same rate?
It's going to deform.
It's going to deform, right? It's going to twist. It's going to contort in two different directions sometimes. So if you had a straight piece of pipe and something's just going to basically twist it like that, what do you think is going to happen?
Snap or break or something.
It's going to snap or break.
A break.
Exactly. So remember, just because we're thinking that things are not going to move, we have to remember everything is dynamic. It all moves, right? Sometimes at different rates, especially on the longer ships. This might be physically attached to a bulkhead and not actually a piece of equipment, all right? And that's going to move like hell compared to what is happening as far as equipment. All right, when you guys get out on sea term, go down to that shaft alley when there's when we're in some rough seas. You'll see the entire thing shifting and turning in almost two different ways. All right, it's pretty cool. So this is all correct. It gives its room for the external forces that's going to be applied, and also on the internal for the system. All right. So tubing connections, we got brazed, all right, or sweating. So has anybody here done any sort of soldering, whether it be electronics or with any sort of like copper tubing?
Microelectronics, like little things, yeah.
Electronics. So when, and the big thing is you do copper tubing, you'll understand this, same with soldering, all right? So when you're soldering two pieces of wire together, all right, and they're all that stranded wire, right, on both sides. And you want to solder these two things together, right? You twist them together, all right, so they form like a bundle, right? Now here's the big thing. How do you know the solder is going to get everywhere? Because that's what you want. You want a really strong electrical connection. You don't want just the outside to be soldered. You want solder within the entire thing because you want the electricity to pass through. If it's a 12 gauge wire, you want electricity to pass through the entirety of that 12 gauge, not just the outside or where it's making contact. So we're trying to make a physical contact here. What do we use?
Yeah, flux, right?
Use flux, right? And flux has a great property to it, all right? Who here has used flux with any sort of piping connections when you do soldering there?
I have.
You have what? What does it do when it heats up?
It gets sucked into the thing that you're trying to braze.
It gets sucked in. It goes to heat, right? It turns to almost a liquid, right?
Yeah.
So when you put it on, it's almost like a gel, all right? And when you heat it up, it turns into a liquid. It flows, all right? And then it eventually boils off. But what's nice about it is that the solder, the actual solder that you use, will follow the flux. That's what the flux is designed to do.
Yeah, it gets carried, or the solder gets carried by the flux for like microelectronics and stuff. That's
exactly. All right, so if you dip both sides of these stranded wires together, right, and then you twist them together, now they're totally encased in flux. You heat that stuff up, all right, that flux starts to boil, it starts to become a liquid. You add your solder to it, all right, and now that solder is going to follow wherever that flux is. It's going to heat up, all right, it wants to go to the heat. And now you're going to have solder all throughout inside of there, right? Just because of the flux. All right. Does that make sense? It's the same idea when you're doing piping. But instead of all those little strands, we're trying to make sure that our soldering material goes everywhere on this pipe. We want to make a nice solid connection. Unlike welding, where welding was happening here on the outside, and yes, it had some penetration into this area. We want solder to go all within this, right? And it makes a really solid connection.
I know with like electronics and stuff, usually like you put the solder on the bottom of it and then feed from the top. I mean, you put the iron on the bottom and feed from the top the solder, and like it travels to where the heat is because of the flux. And do you do the same thing with like copper tubing and stuff? You heat it up kind of where you want it to go and it follows in?
Exactly. So you want to heat up around the whole pipe to have the whole pipe be hot. But when right before you actually add your solder to it, you want to place it on the bottom or on the farther part of the pipe. And then you add the solder to the top and then let it flow to the heat. Right. So it encompasses the entire thing. It wants to go to heat. All right. So exactly right. So if we look right here, the tube is heated and expands. The flux is forced out of the clearance area and brass alloy contacts the tube. The fitting is heated and the clearance area opens. The flux and alloy flows out. All right, and it'll follow that flux because that flux is trying to boil off right now. All right. Both the tube and the fitting are now heated as the alloy flux is basically penetrates the entire area. All right, so the same thing. It's basically what you're trying to do is you heat the entire thing. As that flux starts to boil, you're going to add your solder. All right. And because this fitting is thicker than the pipe, you want to heat that more. All right. And heating that more will allow, when you put that solder into it, that solder will follow that flux and it will fill that entire crevice. All right. Again, this isn't a welding class. Just know that we are going to basically, for sweating, flux, and all that idea, what that is there for. All right. Not so much the method, but why.
Quick question.
Yep.
What kind of piping would we usually use stuff like that on? Because it sounds like it's kind of more of an electrical thing.
It's used on copper. All right.
Oh.
Pretty much exclusively copper.
Okay.
All right. I was just bringing up the electronics is because you can see when you think about it, when you're putting all those little tiny wires together, you would have a crevice there that nothing would get into, and flux would flow into all of it because it turns into a liquid. It's the same thing on the outside of a pipe. If you have all this flux on the outside of your pipe and you heat it up, that will start to become a liquid. And then as you add the flux to the outside, that's my flux stick. All right. Well, it becomes liquid. Gravity will flow, and it will flow downwards towards the heat, and the flux will go that way. The solder will follow it. All right.
Okay.
The wire analogy was because you can have that whole wire. Basically, it's the same idea. It's just using a different type of solder for a different application.
But we're not using wires here, any kind of electrical equipment. This is just for piping.
Yep.
Okay.
It's more to picture it. If you were to have those pieces of wire, how would you be able to penetrate deep into it? All right.
Gotcha.
So we also have flare fittings. All right. This is my flare fitting tool that I have right here. All right. It's the same thing as the one in the picture. All right. So this one right here is what physically will flare it out. You can see that it has a concurve. It has a flange to it right deep in there. All right. Now, this is the tool that goes on top of it. All right. You can see that it has a taper to it as well. All right. put these two pieces together with your tube inside of it, all right, your copper piece of tubing. And those two pieces will now flare out, all right, whatever copper is in there. All right, it will push the material and actually force it to become flared. All right. So you can see that it will flare out this tube right here and here using those two tapers. All right. Now, a lot of engineers don't like these. All right. Why do you think we wouldn't like these as engineers? They work for a little while, but they don't work as long as other pieces of equipment out there.
Does it create weakness in the bend?
Exactly. We're not adding any material here, right? So when we flare this out, we are stretching that material. We're going from a 3/4 inch piece of pipe down to a 1 inch piece of pipe on this flare. All right, so we're stretching it, we're manipulating it. All right, so we can have a failure point pretty much right on this actual physical flare, not due to the fitting, but due to the actual copper, the material here being stretched and pulled and manipulated. All right, so that failure can happen pretty much right here. It can penetrate through this way. All right, so a lot of people don't like these. Now, this is different than if anybody does any home plumbing, right? Look at where the water connector goes to your toilet, right? Or underneath your sink. It utilizes a flared fitting, but that's the difference. It's a flared fitting, all right? The actual fitting is the flared connector, not the pipe. All right. What's making the actual seal here is the pipe being squeezed down on a flare. Whereas if you use a actual flared fitting to connect the two pieces, that's two tapers making a seal, which will last forever. It will be fine. But because we are manipulating and we are stretching and almost damaging the material, the tubing itself, that's where this becomes different. All right, you understand the two differences between them, right? All right.
Not really. You go over that again.
Okay. So if you have an actual fitting, all right, let me see if I can pull one up real quick. Trying to find a good picture. Give me a second. There we go. And here we go. Yeah, that's good. All right, so this is a fitting that you would see down on your home plumbing, which is different than the flared fitting that we saw on the PowerPoint. All right, you can see that it has a flare to it, right? It has a taper. But what's happening is it's not, the actual piping itself isn't being manipulated.
Okay, now I get it. Yeah, yeah.
All right,
It was designed that way.
exactly.
Yeah, okay.
So if we look to our PowerPoint, we can see that we actually had a manipulation done. That right there is our failure point. All right. Not a lot of people use these anymore. All right. Like I said, they're quick, good fix, but they just won't last as long as other options out there. All right. So if you have to, use it, but always remember to go back and fix it. All right. And then that nut will come back down and it'll squeeze it and it'll make it a nice tight connection. All right. So got another 14 minutes before we're going to do our quiz. We can get through these. So we have a welded, brazed, flanged, or threaded connections. All right. These are our pipe fittings. This one right here is a cap. The cap uses internal threads to cap off and stop the flow. And then we have what's called a plug. A plug uses external threads to stop the flow. All right. Now, if we have two pieces of pipe that are equal size that utilize internal threads, but what's called a nipple. Those have external threads that screw into both sides of the internal threads of your piping. All right. These can come all the way up to 6 inches, and they can be down to a little bit of a 1/4 of an inch. All right. Next up is a coupling. The coupling uses internal threads to connect to the external threads of your piece of pipe. All right. Now, this is called a union. Unions are made up of 3 pieces. All right. If we think about it, they do the same job as a coupling. Now, what happens if I rotate this coupling this way to tighten down onto this side, on side number 2? What's up?
If you tightened it towards number 2, wouldn't you loosen it off number 1?
Exactly. But that's only if number 1 is structural into the wall or if it's attached to another piece of equipment, right? If this number 1 can free spin, then it's fine. Use a coupling. But this is where unions come into play. What if this happens a hell of a lot, all right? You have 2 pieces of pipe that are connected to 2 different walls like that, or a piece of equipment and into a wall. All right, but you got to connect them. And if you use a coupling, one side's going to tighten, the other side's going to loosen. All right, or it's not even connected to a wall. There's just 30 feet of pipe that you don't want to remove for it to free spin on side number 1. All right, in order to attach a coupling. All right, this allows you to break into 2 pieces. All right, it utilizes 3 pieces. One gets screwed onto here. The other gets screwed onto the other side. And our third piece, which is the collar, screws both of those together, utilizing these threads right here. All right, it makes a metal-to-metal contact to seal. All right, that taper right there and there is what seals it. I have some actual pictures that you'll see. All right, after we finish this PowerPoint.
Is that like the P-trap under a sink? Like they have it's like a coupling like that?
P-trap uses basically, it's not really a coupling, but yes, at the same time it could be, because it's not really technically 3 pieces. It's that U-bend is one side of the piece. So yeah, yes and no. All right, so it's a run of piping that can be opened without the removing of large sections of pipe. All right, so you can break 2 sections of pipe utilizing a coupling. All right, if we want to connect 2 pieces of pipe that are unequal in size, we use what's called the bushing. All right, it has external and internal threads. All right. Now, if we have a different, so maybe we need to go from something that has a external thread to external thread, but they're two different sizes, we can use a bell reducer. All right. So that utilizes internal threads on both sides to connect the two pieces. All right. Remember, all of these things are being connected. The only thing that's metal to metal contact, right, it's a metal flush to metal flush seal, is our union. Everything else is basically sealed by threads. We want to connect multiple pieces of pipe. Yep.
With the, can you go back on that one slide? I'm sorry. The bell reducer, does that gap stay like that, or does it actually connect?
Yep. So there's always this gap here. All right. I have a picture that I'll show you guys that actually has physical bell reducers, but these threads are what's making the seal. All right. These two pieces of pipe will never make contact with each other. All right. See it like right here, they're not making contact on the actual bushing. They're making contact via the threads, and that's what's physically making our seal.
Now, do they have unions that are also bell reducers in case like those two pipes are fixed?
Basically what you would have to do is you have to cut it farther back, thread it, and then you'd have to do a union plus a bell reducer to get to the proper size.
Okay.
All right. That would be like extreme specialty equipment. All right. I'm sure it's out there, but it would be really specialty. So if you're going to connect multiple pieces of pipe together, because God knows that you're not just going to have the one straight long piece of pipe forever. All right. We have what's called a T that does 3 different pieces that can join. All right. We have a reducing T, which one side is going to be smaller than the other. So if you want to say like add a piece of chemical to, you know, the flow of water or what have you, a lot of these times the reducing T will be, you'll have like a 1-inch piece of pipe over here and it'll split off to 2 1/2-inch. All right. So you get even flow going into both directions. All right. So you can see that as a reducing T. All right. You can have a side outlet T. So this has this has 4 different areas where it can actually have fluid coming in or out. Again, here's a cross. It has 4 as well. We can have a Y bend or a Y branch. You see these all the time on firefighting equipment. So look to the ship. One side will be connected to a hose. The other side will just be there. All right. And then we have a side outlet elbows. This has 3, I pressed the button wrong again. This has 3 different places where fluid can enter or leave the system. We want to change the flow. All right. The direction, we have elbows, and we have what's called a street elbow. Street elbows are pretty much very specialty used. All right. Most of the time you'll use an elbow like this. All right. Street elbows can be used in a spot that you don't have as much space. All right. So if you don't have the physical room to have an elbow on the outside, like this big piece of material here, this goes inside of the pipe. All right. Like that. So a lot of the other times is that you don't have the vertical height either. All right. This distance to this distance on a regular old elbow is longer than this distance to this distance. All right. So it gives it just a little bit more short, and sometimes that's all you need.
Excuse me?
Yes.
Is that threaded on the bottom? So like how would you tighten it if it was threaded?
This is going to be right here is threaded in.
So like
right? So you basically screw it in until it achieves the correct direction that you want it to be.
If there wasn't like enough space for the regular elbow, then like how would you have enough space to screw it? You know?
It would be well, if you're in that where it's like say like a little tiny corner, then you're really screwed. That's soldering time.
Okay.
But it's more about the space. Like maybe you have a piece of pipe that's rubbing up like right here, where this can still free spin, but you can't physically get it because there's that pipe right there.
Okay.
All right. So it just allows that area where you may not be in a spot where that little bit of material there, you just can't have it. All right. And of course, these elbows come in 45, 30s, reducing all the other things that we saw already. All right. We have U-bends. All right. We have a U-bend with a back outlet. All right. So that outlet could be like, a little bit of fluid going that way. Or again, if you want to add like maybe a chemical to a water stream. And then, of course, with tube fittings, it's literally all the exact same as pipe fittings. All right, they come in all the same shapes, sizes, all that other fun stuff. All right, one last thing before we begin this quiz. Resume, there it is. Share screen. All right, so here's on Grainger's website. All right, so piping. You can see that it can come in. Here's schedule 80 pipe nipple. All right, you can see how small that is. All right, it comes in all of these different nominal pipe size. So you can see it's 1/8, 3/4, 1.5. All right, here is more of what you could see of schedule 80. Comes in 1/8, 3/4. All right, you can see the overall pipe length. You can choose a different pipe length. All right, the longer you get, the more you have to figure out what you're going to be getting. All right, so this is stuff that you have to look at for when you're ordering. All right, here is fittings. All right, like I said, you can have fittings that can have this little hex on here. Count your lucky stars if you get that, because then you're not ruining your threads when you're trying to tighten these things in. Because most of the time, what you'll end up with is something down over here. All right, that will be probably your last one, and don't ruin the threads because it's not going to make a seal. Good luck. That's basically what you'll have. All right. But like I said, they'll pretty much come in this size all the way up to 6 inches, all the way down to this. All right. You'll have basically a Venmar full of all of them, all the shelving unit. All right. Here's some unions that I've tried to find that are cut in half. This one utilizes a gasket. All right. An O-ring in there. Most of them will not. It's the only one I could find right now that utilizes a cut in half. All right. So this is what they actually look like most of the time. As you can see, it has that slight taper, and that's where it's making that contact. So you have piece 1 right here, piece 2 over here, and then that collar on the outside that pull both of them together. All right. Here's another same picture. It just gives that little bit. This is what I was looking for. There you are. All right. So you can see that contact that these make right here. Right where my arrow is going over on both sides. That is where that physical contact is being made. All right, you can see it right there perfectly. I'm gonna post these onto Blackboard so you can take a closer look at them. All right, all of those. Here's some couplings. All right, here's some different plugs that you can end up with. Again, with the caps, all right. And then here's your bell reducers. That's what I wanted to really show you. All right, you can see how they have those internal threads. All right. So that is it on the show and tell on that. All right. We have a quiz today, class Wednesday. There's no class Monday. All right. With that, we are going to be talking Monday about how lab is going to start on. We're going to be talking Wednesday on how lab is going to start on Monday, okay? So be prepared for a quiz on piping on Wednesday as well. All right, I'm going to post the PowerPoint this afternoon. All of the YouTube videos are going to be posted as well, as same as all of the fittings that I showed. All right.
Professor, will you be posting the lecture?
When will I be?
Will you be posting the lecture?
I'm going to be posting it to the YouTube channel. All right. So right on the announcements, you can find it there. After you're done with the quiz, you guys can leave. Just make sure you just kind of don't say anything, just so that way you're not disturbing anybody else who still needs to take the test. All right. And then make sure you get those forms signed and submitted. All right. Like I said in the beginning of lecture, Don't make me chase you. If I have to chase you, I might start making it worth points just for fun. Okay? For me, not for you guys. All right, let's see. Everything is all good. Yep. So at 1 o'clock, you'll see your results. All right. So that way, anybody who is still taking it will have that full time. All right. Test should be open. You guys should be able to see it for the quiz. Oh, and this goes without saying, it's not open notes, no cell phones.
I have a question.
Yep.
Yeah, so on one of the questions,
Lost you.
question 3.
Okay, just give me 1 second.
Oh, it just says what valve below. Okay.
All good?
Yeah.
When we finish, are we allowed to go?
Yep, you're allowed to go as soon as you're done.
Have a good one, Professor.
Have a nice day.
Have a good day.
All right. Have a nice weekend.
Have a nice day, Professor.
Thanks a lot, Professor. Have a good one.
Have a good day.
Have a nice day, Professor.
Take care, Professor.